This is Alan Elliott, and this is SAS Essentials, Mastering SAS for Data Analytics, 3rd edition. This is Chapter 17, Logistic Regression. In this chapter, we'll be able to perform a logistic analysis using PROC Logistic, and we'll also be able to create a SAS program that will perform a simple logistic analysis, and also perform a multiple logistic analysis. And also, we'll look at ways to SAS can assess the model's fit and predictive ability. As usual, if you'd like to follow along with the examples in this chapter, be sure to download the files from this location. Let's get started. Let's look at model types before we get into logistic regression. And this is just to sort of review the model statement in SAS, which is model dependent variable equal independent variables. I just wanted to point out that this model statement is used in a number of PROCs in SAS, and they tend to mean slightly different things. Like in PROC-ANOVA, the dependent variable is a grouping variable, and the independent variables tend to be quantitative. In linear regression, the dependent variable is continuous, and the independent variables are quantitative or grouping. In logistic regression, the dependent variable is binary, and that's the way we're going to be looking at this in this chapter, where the independent variables are quantitative or grouping. And also in chi-square, although we don't use a model statement, we have grouping type variables in both situations. Look at Appendix C to see how you would choose what analysis to use in various situations. All right, let's look at binary logistic regression. So binary logistic regression models are based on a dependent variable that can take on only one of two values, such as the presence or absence of a disease, deceased or not deceased, married and not married, and so on. In this setting, the independent, sometimes called the explanatory or predictor variables, are used for predicting the probability of occurrence of an outcome, such as mortality, dead or alive. Now, we're going to look at just briefly look at this basic form of a logistic equation. We're not going to really go deeply into this, but what I want to point out here is that we have one or more independent variables represented by the x's up there, x1, x2. And p is the probability of occurrence of the outcome of interest. So from the independent variables, x1, x2, and so forth, we're going to try to develop an equation that will give us the answer to p, the probability of occurrence, which is going to be somewhere between 0 and 1. And also as in linear regression, the parameters of this theoretical model are estimated from the data. All right, so let's look at the hypotheses for the logistic regression. Any variable with a 0 coefficient in the theoretical model is not useful in predicting the probability of occurrence. So as we looked at, let me back up just a minute, on this equation, notice just like in logistic we have beta 1, x1. So what we're trying to calculate is this beta 1. So we have beta 0, beta 1, beta 2. So we're trying to estimate the value of beta. If that's 0, what that means is that coefficient is not useful to the model. So if this null hypothesis is not rejected, then no statistical evidence that the independent variables as a group are useful in prediction. If the overall test is rejected, then we conclude that at least for some of the variables are useful in the prediction. For each beta equal 1 through k, the SAS reports the results of the test. So here are the hypotheses. So in simple logistic regression, we have the null hypothesis beta equals 0. So in this case, the ith, or really there's only one in this case, independent variable is not predictive of the probability. In other words, we're predicting if beta is 0, then there's no predictive value. And the null hypothesis is that beta is not 0, therefore there is some predictive value. All right, another topic that we need to talk about when we're looking at logistic regression is the odds and odds ratio. So another use of a logistic model is the calculation of what's called odds ratio, OR, for each independent variable. The odds of an event measures the expected number of times an event will occur relative to the number of times it will not occur. Thus, if the odd ratio of an event is 5, this indicates that we would expect 5 times as many occurrences as non-occurrences. And odds of 0.2, which is 1 over 5, would indicate that we expect 5 times as many non-occurrences as occurrences. And you can see the text for a lot more information on interpreting the odds ratio. So let's look at performing a logistic analysis using PROC Logistic. So PROC Logistic is a SAS procedure that allows you to analyze the data using a binary logistic model. An abbreviated syntax is shown here. So we have PROC Logistic, and we have some options. Then we have a class variable. Now, class variables are the categorical variables such as male, female, etc. Could be cancer stage 1, 2, 3. And then the model statement. In the model statement, the dependent variable, this is what makes logistic different. The dependent variable is binary. Early in this discussion, we talked about various ways that the dependent variable could be used. But in this case, in logistic, the dependent variable is binary. It can only take on 2 values. And then just like in the regular regression, we have variable options and so forth, and independent variables listed. Okay, so what are we predicting? So by default, SAS assumes that the outcome predicted with P in the logistic regression corresponds to the case in which the dependent variable is 0, or the lowest number in the alphabetical character. This will be explained more as we go along. But for example, if we have a dependent variable such as disease, and we have it coded where disease equals 0, indicating the disease is absent, and disease equal 1, indicating the disease is present, SAS will predict the probability of disease absent by default, because it, again, goes in numerical or alphabetical order. So 0 comes before 1, therefore by default, it's going to predict that the disease is absent. And we'll see how to change that, because that's not always what we want to do. All right, so let's look at some common options for PROC Logistic. Data is, we're familiar with that. Descending reverses the sorting order for the level of the response variable, and that's going to come in very handy. By the default, as we mentioned, the procedure predicts the outcome corresponding to the lower value of the dichotomous variable. So if the dependent variable takes on the value 0, 1, then by default, SAS is going to predict that the dependent variable is 0. Unless we use the descending option. And we'll see that in an example coming up. The alpha value specifies a significance for confidence limit. No print suppresses output in case we're trying to just calculate it for some other reason. Simple displays simple descriptives. And plots allows us to ask for some plots. Also, there are some common statements for PROC Logistic. We've already seen the dependent variable, the model statement, dependent variable equal independent variable. The class statement, which specifies which variables are classification kind of variables or categorical variables. The odds ratio label creates a separate table with odds ratio estimates, and we'll see some examples of that. Output creates output data set for the predictors, and then the common ones by format, label, and where. Now, the descending option in the model statement is used this way. So if we have PROC Logistic model equal dependent variable equals independent variable 1, 2, etc., we have to really take care, and I've emphasized this from the very beginning, we have to take care of what how the dependent variable is defined. And we've said this before, but I'm just continuing to emphasize it. For example, if your dependent variable is fail, 0 means not failed, 1 means failed, then SAS is going to predict fail equals 0 because it's the lowest value. If we wanted to reverse that prediction, then we use descending option. And so you see the slight change that I have here now in the procedure, PROC Logistic descending. Now when we do that, we're going to predict fail equal 1, which is oftentimes more likely what we want to do. Another way to specify what is predicted is to use this kind of coding, where we say model fail event equal 1 equal independent variables. That specifies that what we're trying to predict is an event equal 1, so fail equal 1. And this causes SAS to use 1 as the value for the model of the dependent variable fail. We recommend that you choose to either use descending or the event option to specify the value of the response variable, what to predict. And also, if you use this fail event equal 1, then it makes it super clear exactly what you're trying to predict. All right, let's look at some common model statement options for PROC logistic. Again, this is within the model statement. We can have the option EXPB, which displays the exponentiated values of a parameter, which actually are the odds ratios. Just like in the regression, we have a selection type, which specifies the type of selection we want to use, stepwise, backward, forward. We explained that in the chapter on regression, simple linear regression, or multiple linear regression. SL entry, SL stay, again, is very similar. Lack fit is a option that requests the Hosmer Lemeshow test that we'll describe later. The risk limits request confidence limits on the odds ratio. The C table requests a classification table report, and we'll see an example of that. Include equal N, if we have multiple independent variables, it includes the first however many we list there. For example, if we say include equal 1, then the first independent variable is going to be automatically used in the model. And then out ROC outputs the ROC values for a data set, which is the operation characteristic curve value. All right, so let's look at the selection option. The backward method considers all predictor variables to begin with, and then starts eliminating them one by one. I'm not going to go over this in detail because it was the same for multiple linear regression. The forward starts out with nothing and moves forward as we add ones that are important. Stepwise is sort of a mixture between the two. It will add new things, but it will also take things away if they become no longer significant. So this is the typical model statement, how you might do that. We say model y equal x1, x2, and so forth. And then slash, now this is where the options come from. So we saw the option EXPB, and then here's the selection. Selection equals stepwise. We specify the entry and the stay values. And then we have the class statement. Why do we need that? So if a model includes an independent variable that are categorical, then we use a class statement to indicate which values are categorical variables. So in this code here we say class catnum, catalf, which are two categorical variables. And you can see now we specified them in a class statement and then used them in the model statement. So if we're going to have a categorical variable in the model statement as an independent variable, we need to tell SAS or the PROC logistic that those are categorical variables. Otherwise, it's going to try to treat them as numeric quantitative variables. Okay, let's talk about how logistic handles categorical variables. So when a variable is defined as a classification variable, SAS actually sets up something called a default parameterization of n-1 comparisons. And by doing that, what it's doing is setting up a way to calculate the odds ratios with a default reference value to which the other categories are compared. For example, if race categories are AA, H, C, and 0, then odds ratios are reported for AA, H, and C based on the reference to 0, thus AA to 0, H to 0, C to 0, since 0 is the last ordered or alphabetic value. Similarly, if race is defined as 1, 2, 3, 4, 5, then then 5 is the last value, so the odds ratios are going to be compared 1 to 5, 2 to 5, 3 to 5, and 4 to 5. We can change the reference category by including an option statement ref equal value. So after the name in the class statement. For example, the statement class race ref equal AA makes AA the reference value rather than O. And also look at the text for more details on this on this setup here. Another way to handle categorical variables that some people like to do is to create dummy variables. Instead of having a variable where you have a race 1, 2, 3, 4, 5 or AA, H, C, and 0, what what they do is create categorical variables where you're either African American or not, Hispanic or not, Caucasian or not, and to do that we use if statements. So if race equal AA, then we're creating a new variable called race A equal 1, else race A equals 0. So now we have a new variable called race A, and we use that in the model instead of race. So we'll have race A in the model, race H in the model, race C in the model. And this sometimes creates odds ratios that may be a little bit more easier to understand. All right, so let's look first now at a simple logistic analysis. So a simple logistic analysis is one that only has one predictor or independent variable. The predictor variable can be either binary or quantitative measure. So here we have a simple logistic code. PROC logistic data equal, in this case we're using a data set called accidents. We have using the descending option here, and our model is dead equal penetrate. Now from this data set, accidents data set, what this is it has this variable called penetrate, which is a 0-1 variable. Now what this means is, did the patient coming in have a penetrating wound or not? Penetrating wound would be 0, not would be 0. Penetrating wound would be 1, not would be 0. So we're trying to predict the probability of a person dying as to whether or not they had a penetrating wound. And then we're also asking for this slash risk limits to request that the odds ratio be output. Okay, so let's look at this as an example here, example 17.1. Open the program file called alog1.sas, and we see the code here. It's just the same code as we were just looking at, where we're looking at accidents. We're trying to predict death according to whether or not someone had a penetrating wound. So in this example, the independent variable penetrate, which is a 0-1 variable, is used to predict death, dead equal 1. So the descending option is used. That is, since dead is a 0-1 variable, if we didn't have the word descending, it would predict death equal or dead equals 0, which would mean they were alive. That's not what we're trying to predict. We want to predict whether or not the penetrating wound would predict dead, so dead equal 1. That's why we're using the descending option in this case. So we're going to run the program, and when we do, pay special attention to the statement in the output that says probability modeled is dead equal 1. That's what we want to. We want to make sure that the model that we're looking at is predicting exactly what we're trying to get at. So this indicates what is modeled. Make sure it's the output you want the model to model. In this case, we're predicting death, so we want it to say dead equal 1 is what we want to model. Also, let's look at the response profile. This tells us how many subjects are in each category. So in this case, we notice that there are 103 dead and 3580 who were not dead. So we have quite a few more alive than dead, which I guess is a good thing. Let's continue to look at the tables here. So our primary tables of interest in the output are the estimates of the model. So this is similar to an ANOVA table, but we're looking for penetrate. That's what we're trying to predict whether or not, or if you remember back to the model, we're trying to see if that beta is 0 or not. That's a null hypothesis, the beta is 0. And so if we have a p-value, in this case less than 0.001, we are saying that there is evidence that penetrate is a good predictor for dead. And then we look at the odds ratio. And here we have, again, penetrate. The odds ratio is that estimate there, 3.56. So the odds ratio gives us an idea of the strength in predicting the outcome. In this case, the odds ratio, again, is 3.56. Now, if we change dead equal penetrate to dead equal ISS, which is a continuous variable, then we're going to see a little bit different answer here. Again, we're still dealing with a simple logistic analysis. That is, we only have one independent or predictor variable. So notice here, the only change I've made here is dead equal ISS. So instead of predicting from whether or not it was a penetrating wound, we're going to use this ISS, which is an injury severity score which is a continuous variable. So instead of a 0, 1 variable, ISS takes on a number of values. So it's a numeric value, a continuous variable. So this is going to be a little bit different. So if we run this data, or this model, we see that we get similar tables here where we're interested in the first table, ISS. Is that a good predictor of dead? And again, we get p less than 0.001, which says that ISS is also a good predictor of death. And then we have the ISS odds ratio estimate of 1.111. Now, we need to pay special attention to this odds ratio and the odds ratio from the previous case. So let's take a look, dive a little bit deeper into that. All right, we did these first two examples on purpose, first looking at a dichotomous and then using a continuous variable as predictor variables. And this is an important concept that you need to really pay attention to, and that is that the odds ratio is interpreted differently for penetrate than for ISS, as ISS is a quantitative measure and penetrate is a binary measure. So you need to pay close attention to this difference, because I see people getting this mixed up all the time. So I think it's something you need to pay particular attention to. So for penetrate, which gives us an OR of 3.56, indicates that the odds of a person dying who had a penetrating wound is 3.56 times greater than for a person who did not suffer this type of wound. So that's a pretty simple interpretation. Again, penetrate is a binary 0-1 kind of, or 1-2 kind of variable, whereas ISS, so for ISS, which is a continuous variable, gives us an OR of 1.11. And this is interpreted, as I say, a little bit differently. 1.11 indicates that for each unit increase in ISS, the odds of dying increases by 1.11 or 11%. So hopefully you can see the difference here. And particularly when it's a continuous variable, it's maybe a little bit more difficult to interpret, but you need to keep in mind that in a continuous variable, the odds ratio indicates that for each unit increase in whatever that variable is, then that predicts whatever we're trying to predict, in this case dying. So when OR is less than 1, so we've been looking at this, and OR has been greater than 1 in both of those cases, but an odds ratio less than 1 can also be important. For example, suppose a significant OR in this data set, say age, was 0.89. So how would we interpret that? That would be interpreted as, and again, age is a continuous variable, so for each increase in age year, the odds ratio of dying is less by whatever percent, in this case 11%, which is 1 minus 0.89. So one way to look at it is variables with a high odds ratio are predictive of death, or for whatever the predictive outcome is, and variables with an OR less than 1 are protective of death, or whatever the outcome is going to be. All right, so let's look at graphing some simple logistic results. And this is example 17.2. So let's look at, open the program file alog2.sas, and you'll see this code, where we first have a PROC logistic, where we're looking at that model that we saw earlier, where model dead equal ISS, and then we added some stuff here in red. The output, out equal log out, predicted equal PROB. And what we're going to do is we're going to output this data so that we can then graph it. So after we've done the PROC logistic, notice here we have a PROC sort to get the data in the correct order. So we're going to order the data in the file that we created called logout by ISS. We're sorting it by ISS, and then we're going to do a PROC gplot on that same data set, and we're going to plot the probability by ISS. All right, let's take a look at the output from this. Some of this is going to be something we've already seen before, but some of it is new. First of all, let's look at this top table. These are just sort of informational tables. You just need to look at it and make sure that the outcome that you're going to be getting is based on the correct data. It's always good to look at the observations read and used. The response profile, again, 103 people dead, 3580 not. And the very important option, probability model, is dead equal 1. Also, here we've seen this output before, but ISS, again, is an important predictor, p less than 0.001. Also, pay attention to this estimate column. And we're going to use this information in just a minute. But notice negative 5.44 and 0.1056. And then, again, the odds ratio we've seen down there is 1.11. Now, those numbers, negative 5.44 and 0.1056, are actually the numbers that are used in the predictive equation. So the logistic regression is based on estimates given in this maximum likelihood estimate table is, and we can see here our prediction of p hat, we call it, is the prediction calculated for the value of ISS. So therefore, what SAS is doing sort of behind the scenes, or we can do on our own, is we plug those values, negative 5.44 and 0.1056, times ISS, and we can create an equation so that we could predict for whatever ISS is observed, injury severity score. So if we happen to be observing subjects coming in from accidents and they're evaluated with an injury severity score, we can predict which ones are most likely to die, and that may help us then triage those that are in worse condition to help them more. So that's the kind of thing that this would be used for. Also, we use the code output here, so we outputted this data to log out, and that contains these values of p hat. So the values in this file log out are those p hat values that we see calculated from this equation above. So here's when we did the PROC G-plot, then this is what we get. Notice on the left-hand side, the vertical axis is the estimated probability, goes from 0 to 1. And what are we predicting? We're predicting death. So, and at the bottom, we have an injury severity score. So if somebody's score is very low, down towards 0, then their probability of dying is very, very low. The higher the injury severity score, then, as we can see by the little X's here forming this line, the higher the injury severity score, the more likely someone is to die. And so again, this isn't a linear line like we would see in linear regression. This logistic regression is more of a curved line. So this is how we would look at it. So let's look at a value, for instance, of ISS, say 50. How would we predict the probability of dying? Well, what we do is we come up from 50, find out where the line intersects, and move over to the left, and we would see that there is a 45.9% chance of death given an injury severity score of 50. So this then becomes a useful plot to predict some outcome, as we can see here. Okay, that was simple logistic regression where we only had one predictive value, one predictor. Let's look at multiple binary logistic analysis. This is section 17.4. So in multiple binary logistic regression model, it has more than one independent variable or more than one predictor. As such, it's sort of analogous to the multiple regression model we saw earlier, where we have many predictors in that case. But in this case, again, the dependent variable is still binary in a logistic case. It's common to have several potential predictor variables, just like in the multiple linear regression. And so we want to know which is the best set of predictors to create what we call a parsimonious or effective prediction equation. So again, similar to linear regression, we use a procedure to select the best independent variables of the set that we have. We can either use manual or automated methods or a combination of both. It's often desirable for the investigator to use his or her knowledge to perform a preliminary analysis of the most logistical or plausible important variables. So that is, the investigator may have a specific reason that they're doing some sort of investigation, and they would typically want to use the variables they have in mind as predictors and see how well that they would perform in this equation. So that would be a manual method. They would say, okay, I want this variable in my equation. But we also can add on the automated procedures, which could be used to select other potential variables. See, the importance of each variable as a predictor in the final model depends on the other variables in the model, and confounding and interaction effects may need to be addressed in certain models. But these topics are beyond the scope of this book. All right, so let's look at hands-on example 17.3. So open up the program called alog3.sas, and we see this code. Now again, we have PROC logistic. Everything looks about the same except where we have model dead equal. In this case, we have multiple variables that we're going to consider: penetrate, ISS, age, gender, systolic blood pressure, and GCS. And we're adding some options here. EXPB, and again, that's going to give us the odds ratio. We're going to use a stepwise selection criteria. Include equal 1 means that we want to include the first variable no matter what. The first variable is penetrate. We have the entry and stay options, and we're going to ask for risk limits. Okay, the first piece of output is similar to what we've seen before, so I really won't go over this. It's the same data set, so this is the same as what we've seen before. The next few tables are the stepwise results. So let's take a brief look at those. So notice here that the first thing it says is that the first things that are included in the model is intercept, which is always in there, and then penetrate. And penetrate is automatically entered in the model because we use the statement include equal 1. And then down below, we verify that penetrate is a good predictor. We already know that because the p-value is 0.001. Now the middle table, which is model fit statistics, we'll look at that later in an example. The sort of a summary of the variables entered into the model using stepwise is penetrate, as we saw, then GCS, the next step selected, then ISS, then age, and then we get the statement, no additional effects met the 0.05 significance level for entry into the model. So it just selected what it thought was the best variables for the model, and then we get this final model table. So here, notice we have intercept, penetrate, ISS, age, and GCS. And the EXP column is the odds ratio, as we see over at the side. Now, in predicting the odds ratio, the intercept, we don't necessarily predict that for anything, but the rest of them, we have some idea already how to predict those. The probability of chi-square, which is the second to the last one, indicates the significance of each variable, and so we see all of those that except intercept, which were again is just automatically in the model. All of those are significant values. We're usually not interested in p for the intercept, as I mentioned. Okay, let's look at then the odds ratio report. So the next table we're seeing is called the odds ratio estimates and walled confidence intervals. So these odds ratio estimates, and actually we saw them in the previous table, but here in the EXP column, but this also includes the confidence limits, which might come in handy. The estimates provides a measure of the importance of the odds ratio. And again, we need to keep in mind as we interpret these that there are different interpretations for binary and quantitative variables. So penetrate is a binary variable, so we know how to calculate what estimate 11.103 means. ISS, age, and GCS are numeric variables, and so we again interpret those in a different way. All right, so let's go deeper and address the model's fit and predictive ability. So once we decide on a final model, you should analyze that model for its predictive ability. One method of analyzing the predictive capabilities is with something called the Hosmer and Lemeshow test. This test is based on dividing subjects into deciles on the basis of predicting probabilities. Now, the text goes into more detail here. Again, I'm just lightly going over what this means. The SAS reports chi-square statistics based on the observed and expected frequencies for subjects within these 10 categories. And we're interested, in this case, we're interested in a non-significant result is what we want. This predicts that there is evidence that the model is predictive. So a little bit different than most tests. All right, so let's look at how we might get that using this next example. So open up the file called alog4.sas. And here we have PROC Logistic, and again we're modeling. Now notice here we're redoing this model, and we're not doing a selection criteria now. We already have determined that these four variables are what we're going to use in our model. And so now what we're doing is looking at some other options here: lack fit, risk limits, and C-table, and the out ROC. So we then made these changes, and now we're going to run this model. So as I mentioned, the Hosmer Lemeshow test is one of them that we're interested in. What we want to see here is a p-value that is not significant. In this case, we get p equal 0.25. So this indicates that the model is predictive. We want it to be non-significant, and so that's one way that we can verify that our model has some validity. So this next table we get because of the C-table request in the code, and this is called the classification table. So the classification table indicates how many correct and incorrect predictions would have been made for a wide range of probability cutoff points used in a model. Typically we use 0.5 or half is the usual cutoff for a predictive occurrence. That is, to predict a non-occurrence of the event of interest whenever p less than 0.05, and to predict an occurrence if p is greater than 0.05. So if we're predicting death, then we look at a value. If our prediction is greater than 0.05, we're going to predict dead. If it's less than 0.05, we're going to predict alive. And if we use that as our criteria, then in this case, 98% of the cases will be correctly classified using the 0.5 cutoff point. Also note that at the 0.50 cutoff point, there's a 38.8% sensitivity and 99.7% specificity. Now, these terms are described more in the text, but this gives you, some people want to adjust those, and so they may go up or down in terms of the cutoff point instead of using 0.05 if sensitivity and specificity, which has to do with false positives or false negatives, is extremely important. We may want to adjust the cutoff point. That's beyond what I'm talking about here, but more information is in the text. All right, again, we asked for the ROC curve, which is the operating characteristic curve, and this is what we get. So it measures the predictive ability of a model. And notice here it has something called the area under the curve, or AUC, as 0.9718. Now, what we want to see is we want to see that AUC value close to 1. If it's 1, it would be a perfect predictor. So anything close to 1 is good. So in this case, we would assume this is now a good fit is indicated. And the AUC statistic is often reported in papers or in research as an indicator of the predictive strength of a model. And when you're considering final competing models, the Hosmer and Lemeshow test and the AUC are the criteria often used. So what I mean by that is, again, the selection criteria for what values go into the model is somewhat of an art. And so sometimes you may consider different models. You may say, well, I like this model with these 4 variables, I like this model with these 5 variables, or I like these ones with 4 different variables. And so you may have several competing models. This would be one way to choose which model you think is the best model. And again, more about this is talked about in the text. All right, so that's a summary of the PROC logistic or logistic regression analysis. And the next chapter is going to be on factor analysis. So if you got something out of this tutorial, I'd appreciate it if you would like and subscribe to this channel, and we will see you next time. Thanks.